Welcome students. In this session, we will be discussing about block cipher design principles. So, during our discussion about classical encryption systems, we have discussed about various ciphers and their corresponding cryptanalysis. Let us summarize those details. Caesar cipher is vulnerable to brute force attack because of its limited key space. And then monoalphabetic cipher is vulnerable to statistical frequency analysis of single letters. And then polygram is vulnerable to statistical frequency analysis of diagrams or trigrams, and hill cipher is vulnerable to known plain text attack, and Wigner cipher is vulnerable to again statistical frequency analysis. And we have made some observation during our discussion about classical encryption system. Thing is, if the key space is small, then brute force attacks becomes easier. So we need to have a larger key size to have a reasonable amount of security. So larger the key size, greater the security. And then we also discussed about statistical frequency analysis. Here, if the pattern found in plain text is being reflected in cipher text. So in that case, we can easily recover the plain text and also the key. So thing is, the smaller block size is always vulnerable to statistical frequency analysis. So we need a larger block size, typically a 64-bit or 128-bit. Now let us discuss about block cipher and stream cipher. A block cipher is one in which a block of plain text is treated as a whole and used to produce a cipher text block of equal length. As I said, a typical block size would be 64-bit or 128-bit. Example for block cipher, there are a lot of block ciphers available. DES, AES, blowfish algorithm, two-fish algorithm, these are some of the popular block cipher algorithms. Stream cipher. A stream cipher is one that encrypts a digital data stream 1 bit at a time or 1 byte at a time. A popular example is RC4 algorithm. Now let us discuss about the need for Feistel cipher structure. Why we need Feistel cipher structure? Typically, a block cipher operates on n bits of plain text block to produce a cipher text block of n bits. So here we have 2 power n combinations of plain text blocks. So for encryption to be reversible, each must produce a unique cipher text block. It is known as reversible or non-singular. It means that we need decryption to recover the plain text. That is the meaning of this point. That is reversible or non-singular. Here you can see in the diagram. So there is reversible mapping and irreversible mapping. If it is not reversible, then you can see here the cipher test 01. It can recover either the plain text 10 or 11. So that is the problem with irreversible mapping. So we need a reversible mapping so that we can recover our plain text properly. And one more thing, as we have already discussed, the plain text block size is say smaller one. That is, for example, let n is equal to 4. Then it is equal to classical substitution cipher. That is, it means that it is vulnerable to statistical frequency analysis. Okay, now let us have the size of n as large. Okay, and we have an arbitrarily reversible substitution between plain text and cipher text, and cryptanalysis becomes difficult. But this is known as ideal block cipher. But the problem is we need to have a key size which is n into 2 power n, and also number of transformation required is 2 power n factorial. This ideal block cipher is practically not feasible in terms of performance and also in terms of implementation. So that is the problem with idle block cipher. So we need some better alternative. It should be practically feasible one. There comes the Feistel cipher. So the Feistel cipher is based upon the idea of invertible product cipher. Here, invertible means we should able to recover the plain test. That is, it should be a non-singular or reversible one. And product cipher means it is a combination of multiple ciphers. Here, the idea is the final result of product is cryptographically stronger than any of the component ciphers. And here we require only a 2 power k transformation instead of 2 power n factorial transformation in ideal block cipher. And Feistel cipher also uses substitution and permutation technique. Here, Feistel cipher uses Shannon's concept of confusion and diffusion. Uh, Confusion means the relationship between ciphertext and key is complex. So we cannot deduce the key from the ciphertext. Similarly, diffusion means the relationship between plaintext and ciphertext is complex. So in order to achieve a diffusion, we use a complex permutation operation. In order to achieve confusion, we use a complex substitution operation. A simple permutation cannot ensure a diffusion. On similar note, a simple substitution operation cannot ensure confusion. It should be a complex substitution and complex permutation. As I said, confusion means the relationship between ciphertext and key is complex. And similarly, diffusion means the relationship between plaintext and ciphertext is complex. So this is Feistel Cipher structure. Here we divide the plaintext block into two halves, right half and left half, and both the halves are subjected to n number of rounds, and then finally we'll be getting the ciphertext block. Here in each round I has an input Li minus 1 and Ri minus 1 derived from the previous round, and we also have a sub key Ki, and it is so the sub key is derived from the original key, the overall key K, and moreover the sub keys are different for each rounds, and also it is different from the original key K. And there is a round function f, and it is applied to the right half of the data, and then taking the exclusive or of the output of that function on the left half of the data. Here in round function we have substitution and permutation. That is, a round function is a product cipher. So this diagram show how it is done. You can see here. So it is divided into left half and right half, and each round we are supplying a sub key K1, K2, K3 up to Kn, and you have a round function also, and finally we produce the ciphertext block. And here we have a separate encryption function and decryption function. So in this particular example, number of rounds seems to be 16, but it can be any number of rounds depending upon the cipher. So now let us discuss about Feistel cipher design principles. So there are various parameters. First one is block size. So if we increases the size of the block size, then the security also tends to improve. But the disadvantage is it also slows the cipher. Then increasing key size also improves security, but again it slows the cipher. And number of rounds, increasing the number of rounds also increases the security, but again it slows the cipher. So greater the block size, greater the security, greater the key size, greater the security. Similarly, greater the number of rounds, greater the security. Then sub-key generation. Uh, okay, from the original key, we will be generating sub-keys for each round. If you make the sub-key generation algorithm complex, analysis becomes difficult, but again it slows the cipher. And round function also, we can make the round function more complex. The complex the round function, the cryptanalysis becomes difficult, but again it slows the cipher. So thing is, there is security versus speed. uh, if security is compromised, you can have a greater speed of encryption and decryption, but as discussed, the security will be compromised, so we need to have some kind of trade-off. But with modern hardware and software, we can have greater security, as well as we can have faster encryption and decryption process. So now let us discuss about Feistel structure and substitution permutation network. So in Feistel structure, we are making transformation to only one half of the data block. Whereas in substitution permutation network, the entire data block is subjected to transformation. Hence, the desired cryptographic effect is achieved in fewer rounds. So that is a great advantage. And in Feistel Cipher, we use the same hardware or same software for both encryption and decryption. That is a great advantage. With substitution permutation network, we will be using a different hardware circuit and different software for encryption and decryption. That is slightly a disadvantage. An example for Feistel structure is DES, data encryption standard, and blowfish, twofish. Those algorithms also uses Feistel structure. Example of substitution permutation network is AES, Advanced Encryption Standard. And both Feistel structure and substitution permutation network uses the operations of substitution and permutations to achieve Shannon's concept of confusion and diffusion, respectively. So, with this, I conclude this session. Thank you.